we're back with some more on limits. And we're going to look at tables and graphs today. Okay, so finding limits using tables. To find the limit as x approaches a of f of x using a graphing utility with a table feature, or we can create a table by hand. Approach a from the left, choosing values of x that are close to a but still less than a. Then approach a from the right, choosing values of x that are close to a but still greater than a. Evaluate f at each chosen value of x to obtain the desired table. Choose values of x so that the table makes it obvious what the corresponding values of f of x are getting close to. If the values of f of x are getting close to the number L, we infer that the limit as x approaches a of f of x equals that limit. So if we look at our problem from yesterday, the opener, all right, remember they're both walking toward x equals 2 and they're going to fall in this hole. Okay, we already figured out algebraically that the limit was 4, but you can tell by tables and graphs also. Well, graphs does. But here's the table. And what they mean by choosing values is when you plug in this function, so I went to y equals and I typed in this function, okay, but then when I went to table set, which is, I do believe, second window, okay, I told it, I don't even remember what I told it to do, but I want to get close to 2, so I think I probably said start at 1.99, and then my delta table, in other words, what to count by, is I counted by what I counted by, I think 0.01s. Anyway, 0.001s. You want this to be really, really small. You don't want to count by ones because it's just going to jump. Okay, you got to count by really, really small, 0.01, 0.001, something like that. All right, and don't start like at -5 and you're trying to get to 2 counting by this small. It'll take you hours to scroll that far. Okay, so start really close to what you're looking at, count really small, and then pull up the table. This they drew it out for you, which is really nice to see. Here's what you would actually see. Okay, but you can see as you're approaching a, well, in this case, as you're approaching -2 from the left, that would be this way. Getting closer, closer, closer. Right before I hit 2, I'm at 3.99999, which is really close. If I'm approaching 2 from the right, in other words, coming this way at it, as I get closer and closer to 2, again, I'm really close to 4. So we would say that f of x is getting closer to 4 from the left and it's getting closer to 4 from the right. So we say that the limit is approaching 4. Okay? Not exactly, and you can't see in here, at exactly 2, you'd get an error message over here. But by what they're counting by, you didn't see the actual 2. Okay, so it says find this limit graphically or using a table of values. So I go and I type this in, and you can use kind of the trace function, and you can say, well, what happens as I'm getting closer and closer to 1? So I just click the trace, and I got as close to 1 as I could on both sides, and it looks like it's around 3. But if I look at the table, okay, at 1, you know it's going to be an error message because if I put 1 in there, and you can see, well, on this side it's going to 1, and on this side it's going to 7. Well, that don't look like the limit even exists then, because it's coming from the left and the right, and they're going to 2 different values. But see, I'm counting by 1s. That's why you've got to set your table to count much, 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 much smaller. So I think I started at 0.97 and counted by 0.01s. I still got my error message, but now you can see as it got really close from this side, it's really close to 3. And as I approach it from this side, it's really close to 3. So we would say the limit equals 3. Okay? This one is continuous. I know it's continuous because there's no denominator. So I can just do direct substitution and say 3 times 4 squared, 3 times 16 is 48. But we're supposed to be using the graphs and tables, so if I graph it, I could just trace and I could get really close to 4 and see what y is close to. It looks like 46 something. Alright, if I look at the table, oh, and here I went a little bit past. Here I was a little bit under 4, here I'm a little bit over 4. So it's somewhere between 46 and 49. So if I go to the table, as I'm getting closer and closer to 4 from this side, and getting closer and closer to 4 from this side, but because it's continuous, I can actually see the actual limit is 48. It's not undefined there. Alright, so if we look at this one, if I graph it, alright, I got this graph, and then I traced it and tried to get as close to 0 as I could, and it looked like it's getting really close to 1. If I look at the table, as I approach, of course 0 is going to be my error, but as I approach, 0.99999 is really close to 1. Approaching from this way, 0.99999 is really close to 1, so we say that the limit is 1. Okay? Alright, so now one-sided and two-sided limits. It says we can see that the limit of the function in figure 10.11, which I should have put on here, but I didn't. It was, I think, x minus 1 cubed over, I don't know, but you get this picture. And it shows this point, and it says x equals 1.0212 and y equals 3.064. If I look at the table of this thing, at 1 there's an error. At 0.999 it was 2.997. At 1.001 it was 3.003. So I'm saying the limit is 3. That's what the picture showed. Whether x approaches 1 from the left or the right. Sometimes the value of a function f can approach different values as x approaches a number c from opposite sides. When this happens, the limit of f as x approaches c from the left is called the left-hand limit of f at c, and the limit of f as x approaches c from the right is a right-hand limit of f at c. And here's the notation we use. You've seen it before. This says you're approaching c from the left. This says you're approaching c from the right. If those two limits are the same, then we say the limit exists. If they don't, then it doesn't. Alright, so it says find the limit as x approaches 2 from the left and the limit as x approaches 2 from the right of f of x, where f of x equals blah, 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 blah. Alright, I'm going to do this two ways. I'm going to do it just using the graph, and then I'm going to do it using algebra. If I'm approaching 2 from the left, that means I'm coming from this way. So as I trace my function, and I'm getting close to 2, this is getting close to 3. So the limit as x approaches 2 from the left, my function is approaching 3. Picture-wise, if I approach 2 from the right, the limit as x approaches 2 from the right, this is the right, so I'm tracing the graph from this side, and as I approach 2, from this side it's getting closer and closer to 1. So, since these are approaching different things, then the limit does not exist. Algebraically, it says I'm finding the limit as x approaches 2 from the left. That means I'm picking 2 from the left. I'm picking values that are smaller than 2. So algebraically, it means to plug in, I have to use this function, negative x squared plus 4x minus 1. If I do direct substitution, I'd have negative 2 squared plus 4 times 2 minus 1. That's going to give me negative 4 plus 8 minus 1. That's going to give me 4 minus 1 is 3. Okay, the limit as x approaches 2 from the right, if I'm approaching 2 from the right, I'm picking x's that are bigger than 2. So I'm using 2x minus 3. So if I plug that in, 2 times 2 minus 3 is 4 minus 3 is 1. Okay, so we say the left-hand limit is 3 and the right-hand limit is 1, but the limit itself doesn't exist. Okay? Alright, so if we look at this one, just using the picture, we have to because they didn't give me a function to use. This says find the limit as x approaches 4. If they don't specify which direction to come from the right or to the left, then you assume it's like a book and you read left to right. Okay, so as I approach 4 from the left, there's 4, my function is getting closer and closer to 7. the value at f is 4, I go to 4 and I find the dot. I don't go to the hole because it doesn't exist there. At 4, there's a dot, which is 2. Okay? And since there's a hole there, I don't expect these to be the same. Okay, so if I find the limit as x approaches -2, again, they didn't specify, so I'm going from the left. As I approach -2, the function is approaching 5. But at -2, the function is 3. Okay, everybody good? Alright, so if I try this one, it says find the limit as x approaches 3 and prove that f is discontinuous at x equals 3. If you get two different values, then it is not the same. Excuse me. Alright, so to find the limit as x approaches 3, if I plug in 3 in the bottom, it's going to, division by 0 is illegal. So I'm going to simplify this up top, and that's going to be x plus 3 times x minus 3 over x minus 3 is going to cancel. So to find the limit as x approaches 3 of x plus 3, I get 3 plus 3, which is 6. The value at f of 2, at f of 3, it doesn't matter what I plug in here, it's going to be 2. Since these do not equal, that means it's discontinuous at x equals 3. Okay? And you can see here, as I approach 3, I'm getting closer and closer to 6. But at 3, it's 2. Since those are not equal, the limit doesn't exist. Alright? Alright, use the graph of the piecewise function to find each of the following. They want me to find the limit as x approaches -2 from the left. So I'm coming from this way, and I'm getting closer and closer to -2, and that gets closer and closer to 0. If I approach -2 from the right, I'm coming from this way, follow, 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 follow. As I'm getting closer and closer to -2, that's -2. It says the limit as x approaches -2. Well, that one doesn't exist, because as I approach -2 from the left, I got 0, and -2 from the right, I got -2. These don't match, so the limit does not exist. And the value at -2 would be the dot, which is going to be -1. Okay? Alright, definition. Limits at infinity. When we write the limit as x approaches infinity, f of x equals L, we mean that f of x gets arbitrarily close to some number L as x gets arbitrarily large, meaning forever and ever and ever keeps getting bigger. We say that f has a limit L as x approaches infinity. When we write the limit as x approaches negative infinity, f of x equals L, we mean that f of x gets arbitrarily close to L as negative x gets arbitrarily large. In other words, as you head off left. We say that f of f has a limit L as x approaches negative infinity. Notice that limits, whether at a or infinity, are always finite real numbers. Otherwise, the limits do not exist. For example, it is correct to write that the limit as x approaches 0 of 1 over x squared does not exist. But, since it approaches no real number L. But, you can see from the graph, as I get closer and closer to 0, this function on both sides is getting closer and closer to infinity. It's just going to keep going up. So we can also conveniently write that the limit of 1 over x squared equals infinity. Alright, and I put some table values here to show that as I pick really small values, I get really big y's. And I even went smaller, and then I went bigger, and yeah, you get infinity. Alright, so if we look at this one, it says let f of x equals sine x over x. Find the limit as x approaches infinity, and find the limit as x approaches negative infinity. Well, if I look at the picture, as x approaches infinity, this thing is getting closer and closer and closer to 0. So the limit as x approaches infinity, the function is getting closer and closer to 0. Same as I go this way. As I approach infinity from the left, my function is getting closer and closer to 0. Okay? Alright, so we are at homework. Happy homeworking, and I will see you next time.